Hello, and welcome to this first series on the InZone webinar. So it's a pleasure for us to organize it. I'm Professor Blanchet from Academic Director of InZone and from the Faculty of Medicine. And we have convened a few experts from University of Geneva to share with us their expertise and to talk about their field. This webinar series is going to be organized throughout the year, and there will be 3-4 sessions per year. We're going to talk about science, we're going to talk about literature, we're going to talk about medicine. So you will have the pleasure to be in contact with some of the experts we have at University of Geneva. The format of this webinar is a 40-minute presentation by our expert. And then you will have a chance during 40 minutes to ask questions or to make comments, and we will try to facilitate a discussion with our expert here in Geneva. You have an interpretation function on your Zoom, so you can get access to interpretation in French. If you click on the hearth icon, you will get access to one of our interpreters from the Faculty of Interpretation and Traduction here in Geneva. But without waiting, I'm going to give the floor to Professor Mayor. Professor Mayor is co-laureate of the Nobel Prize in Astrophysics, and is a professor in astrophysics and has kindly accepted our invitation to launch this webinar InZone series. So thank you very much, and I see you in 40 minutes to facilitate a discussion with all of you. Thank you, Professor.
Hello, everybody. I'm extremely glad to open this session of webinar. So my domain is astrophysics, astronomy, and I will discuss today the problem, the change of ideas happening during the last 30 years in the field of extrasolar planets. So this was a very old question, and we are not the first to discuss this question. So already more than 2,000 years ago, Greek philosopher was asking the question, do we have only one world or do we have others? Do we have an infinite number of worlds in the universe? And still more impressive, in the same letter from the philosopher Epicurus, he mentioned in this letter, do we have as a life, as a possibility of life on others of these worlds? And evidently, this question was also discussed quite by many other philosophers at that time. So what happened today? So we can see that this was not discussed only during the last, in the Greek period, but during the last 2,000 years, you have several philosophers, theologians having discussed this possibility. And now we are entering in the period where science could give answers to this question. So it's very interesting to see that already more than 200 years ago, it was quite common to see some illustration in books for the public, for astronomy, that you can notice that already the artist was mentioning this possibility. In the upper quarter of this book, you can see that the distant stars illustrated in this nice illustration, that you see some stars already surrounded by many planetary systems. So you see this was already quite common for the population, that you see, yes, we should have other planetary systems in the universe. If we move today, right now, to what is happening at OAPEC. As probably you have the occasion to see the Milky Way, this long strip of light on the sky. And in fact, we know that this is the result of some billion of stars. The light are coming from 200 billion of stars. The size of this system is absolutely huge. The light will need something like 100,000 years to go from one side to another one. And the sun is only one star in such a system. Evidently, we cannot go out to take a picture because evidently the distances are much too big, but we can observe other planetary systems or other galaxies similar to our own one. But already we can ask the question, this is not a design, it's really a picture taken with a big telescope, modern telescope, in the center of the central region of the Milky Way. You see, this is a very teeny part of the sky, and already you see so many, many stars. Every small dot here is a sun, is similar to our own sun. So the question we can ask in terms of modern term, do we have planetary system orbiting all these different stars here? It looks very difficult to answer such a question, and evidently it's only the development of the technology having allowed to answer this question. But if the idea that we should have other planetary system in the universe was very common in the population, in fact, it's very strange to see that the astronomers do not believe that we have other planetary system. During the last 20th century, during the first part of the 20th century, in fact, most of the estimation made by the most prominent astronomer said, no, we are alone. Maybe we have another one or two, but this was based on a different error, a wrong theory. And suddenly the ideas changed in the middle of the 20th century, and immediately with this new theory, the ideas jumped to billion, hundreds of billion of planetary system. And today, the observation have completely confirmed this estimation. In fact, planets are only a byproduct of the formation of stars themselves. So this is another galaxies. This is exactly similar to our own one, but it's another one because we cannot go out of our own one. When you look this kind of galaxies, you see that you have small dots, pink dot, along some spiral structure. In fact, it's not stars. Here, it's a huge cloud of gas. When I say huge is something like maybe 100,000 times the mass of the sun. It's a huge piece of gas. And these are the interesting things for what we have to discuss. For example, in our own Milky Way, not far from the sun, maybe at the scale of the galaxies, you have the Orion Nebula. Probably some of you have seen this with good binocular, it's possible to see this. And this is the site of the formation of stars and planetary system. Continuously, you have the formation of new stars and new planets. In 1995, the Hubble Space Telescope, with an extremely high optical resolution, was able to look at the details of stars just formed in this nebula, this big cloud, and going out of this cloud. And with the resolution, optical resolution of the Hubble Space Telescope, you can see on the right side of this image that all young stars are surrounded by a small disk of dust and gas. And this is a nebula to form new generation of planetary system. So you can see the formation of planet is only a byproduct of the formation of stars. So we can anticipate that probably all stars should have a planetary system. The next step is evidently, do we have the capability to see this planet and to detect this planet? In any case, the formation of stars is a very complicated problem. You see this is a huge turbulent set of gas with magnetic field, with a strong difference of rotation, of density, and so on. So this is a very difficult problem. So do we have the capability to search and to detect this planet? So let's imagine how we can see if planets are hosted by such all these small dots you have here. So it's not possible to directly look because the ratio between the luminosity of the star and the planet is so huge that we cannot see the planet itself. Just to have an idea, if you have at some distance of the solar system and you compare the luminosity of the sun and the luminosity reflected by the Earth, it's a factor of 1 billion. So it's evident your eyes is completely dominated by the luminosity of the sun. So we need to have an indirect way to detect. So I will give some ideas of the effect used to search for planets. Maybe you have heard about the Doppler effect. The Doppler effect is an effect related to any source, moving source. Let's imagine this small insect jumping on a piece of water. So in front of the motion, you see the waves are closer together than on the opposite side. So if you know that the insect is jumping once every second, and you are in some direction with the insect coming in your direction, in fact, you can see that the frequency is higher. This is what is called the Doppler effect. It's true for this insect on a piece of water, but it's true for acoustic waves. It's also true for the light. And this is the problem we will use for stars. And the nature help us because in the spectrum of the emitted by a star, in fact, you have a huge number of atomic transitions. And all the game will be to have an instrument precise enough to see the small motion of this forest of transiting atomic transition. So this is possible, but you need evidently to develop a very specific instrument because the change of the frequency is extremely small. And this is what we did with one of my colleagues almost 30 years ago. And we start to measure the velocity of stars similar to our sun. And night after night, we measure the velocity and so on. And suddenly, one of these objects was extremely strange because it exhibits a change of its velocity. At some moment, the star is coming in your direction. In some moments, are receding. And so if you look at the details of the measurement, you see that you have a periodicity of only 4.2 days. So it's very, and the mass estimated for this object perturbing the mass of the star and the velocity of the star was something extremely short. 4.2 days is completely discrepant with what we have. In the solar system, we do not have any planet with a period as short as this. And this is a discrepancy of about 1,000 from theoretical predictions. So, okay, this was an extremely curious object, but just after we have discovered quite a lot of others, and today we have more than 5,000 to 6,000 of exoplanets have been discovered by different teams in the world. So this was the start of a new big chapter of astrophysics is the study of planetary system in the universe. Yes, this is just to say that some colleagues are doing some theory to understand the migration, the fact that the formation of the star, the planet is made at some distance of the star, and then after by different curious physical process, in fact, the planet will orbit and have an orbit tied closer and closer to the star, and with a period shorter. But present astronomer benefits of beautiful instrumentation. Here is not a fancy image, it's real image of an interferometer, a big set of some 60 dishes on an altiplano in Chile at 5,000 meters to observe the cold gas in the universe. So this is a tool to analyze the formation of galaxies, similar to the Milky Way, to the formation of stars, formation of planets, and what is in between. So you can, at some moment, all these dishes will observe one specific point in the sky, and when you combine all the luminosity received from all these instruments, you have the equivalent of a huge resolution, because at some moment you can have 14 kilometers of distance between the extreme dishes. So this instrument was put in operation maybe a little bit more than 10 years. And some of my colleagues at this moment, this is a normal picture of the sky. And you see, you have a small cloud like we saw before. And with this huge instrument, they start to observe this cloud and to see what is inside. And what they discovered, that in fact the star in the middle of this small cloud was exactly as predicted by the theory. You have some ring due to the fact that when you form new planet, you pick all the matter, and this is an image of the formation of a new planetary system. And you see this is directly the proof that the formation of planetary system is only a byproduct of the formation of stars themselves. And you see this, our colleague have evidently continued to this line of research, and you see that all the young stars observed today are surrounded by planetary system. I will go back to my own hobby work, is to search for planetary system by just looking the change of the velocity of the stars due to the influence of the planet. You have the star, you have the planet. Evidently, the planet is doing like this, but the star itself has a small wobble like this. And if you have an instrument precise enough to measure the small change of the velocity, in fact, you can detect new planetary systems. We are mostly observing in Chile, close to the Atacama Desert, and with a telescope, a huge telescope. The mirror is 3.6 meters, and we can detect small change of the velocity at the level of about 1 meter per second, or maybe a little bit better. Let's imagine a star at maybe 100 light years from here. But we have the capability to measure small change of the velocity like this. This is a technical difficulty of this kind of exercise. What is the result of this? We have measured quite a large number. So one night, you measure the velocity of star, you repeat the measurement on the second night, the second week, and so on, and so on, and so on, several years. And for example, in the plot, you can see on the left part of this diagram, you can put one small red symbol, velocity versus time, and after a few years, you have some cloud of of measurements. And then what you have is, okay, we can say that you have a small change like this, or see, okay, we have a planet, a long period planet. But no, if you put all this measurement in the computer and let the computer to analyze these things, you say, no, we have 7 planets. Because if you have one star, what is a bubble? The star will go in your direction, go back, and so on. So the velocity will be something like this. If you have 2 stars, 2 planets, you will have something like this. If you have 7 planets, okay, it's more complicated to show with the hand, but this is something like this. And what is more surprising is the fact that you look on the mass and period. The first one, to the extreme right, left, it's 1 day of period and about 1 Earth mass. The second one is 5 days, 13 Earth mass, and so on. So we have quite a lot of planets with extremely short period, absolutely not existing in our solar system. So this is typical of this domain. Every day we are surprised by something not expected before. This is maybe the most important result of the last 20 years, is the discovery of the diversity of exoplanets in the universe. Presently, we have discovered planets with periods as short as few hours. So they are so close to the star that the temperature at the surface is sufficient to have the lava planet. All the rocks are melted. You have also extremely large planets, 3,000 times the mass of the Earth. You have in the solar system, all the planets have almost circular orbit. We have discovered planets with orbit like this, extremely elongated, and so on and so on. So this is the nice aspect of this. Suddenly we discover the richness of the universe in the field of exoplanets. And a nice byproduct of this discovery. So as mentioned, we have discovered planets with extremely short period. So immediately you see, oh, if you have a star like this and a planet extremely close, we have maybe the possibility to have eclipse. We use the term of transit. So maybe sometimes we cannot see the planet, but what we can observe is a small dip of the luminosity of the star, periodic dip. And at the end of 1990, we made the measurement with some colleagues in Boulder in US, and we have discovered an object with 3.5 days of period. So the planet was extremely close to the star. And exactly at the time predicted, you see that you have the diagram on the upper part of the diagram. You see the small dip of the luminosity of about 2%. So you can immediately measure the relative size of the planet to the star. So the Doppler effect gives the mass, but this gives access to the size of the planet. So it's easy to determine the mean density of the planet, and you discover it's 0.3 gram per cubic centimeter. So it's really very diffuse. It's less than the density of Saturn. So this was really the proof that it was gaseous giant planet. And it was so fantastic that the year after, my US colleague have repeated the measurement with using the Hubble Space Telescope. So when you are above the Earth's atmosphere, evidently the precision you can achieve is extremely high. And you see the diagram in the lower right, that you see the quality you can measure when you are in the space. And evidently, if you have such nice precision, you can say, oh, maybe we can search for much, much smaller planet, maybe rocky planet like the Earth. This was made, this is still continuing, by the the Kepler spacecraft, and having measured. So the idea is extremely simple. The technique is complicated, but the idea is that you have the Earth, you have a satellite like this, you measure a field of stars in the sky continuously during several years. So every few dozen of minutes, you take a picture. You have maybe a picture with 100,000 stars. So at the end of the few years, you have a series of a huge number of pictures, okay, electronic pictures. And then after you look at the luminosity of each of these stars, and you see this sometimes like this, tuck, 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 because you have a planet. But sometimes it's more complicated. It's up. You have multi-deep. And when you analyze this multi-deep, you discover it's multi-planetary system. And this diagram is absolutely fascinating. You have the radius of the object detected, of the planet detected, expressed in unit of the Earth. So the bottom line is 1 Earth, and then this is expressed with the period in days. And you see that they have discovered several thousand of new planets, and all colors code the number of planet part of this different planetary system. For example, if you look the red symbols, it's stars we have 6 different deep, showing that we have 6 planets orbiting, and so on. So multi-planetary systems are extremely rich, very numerous, frequent in the Milky Way, as it was expected as a byproduct of the formation of stars. So now I go back to the velocity measurements. And here, this is one of the instruments we have developed. And this is in the Northern Hemisphere in Canary Island. And this was developed because the Kepler detection was in the north. So we have been obliged to duplicate the instrument. So this is typically a very precise spectrograph. And what we are doing with this, we try to measure precisely the size of the planet as function of the mass. So the mass is measured by the Doppler effect, the size by the satellites, and we have a plot like this. You see that you have different set of lines. And for example, if you concentrate yourself on the lowest red curve, this is the prediction between the relation between the size and the mass of a planet made only by iron. It's theoretical prediction. If, for example, you see the upper one with in blue, this if you have a planet made from only for water. Okay, it's not real. But if you can see Venus and the Earth. This is a mix of metal and rocks, but you can see that all the objects we have measured after up to maybe 5, 6 times the mass of the Earth are rocky planets with the same mixed of metals and rocks as Venus and the Earth. So presently we start to do the physics to understand the formation of planetary system, of planets. And evidently, the wobble of the star due to the planet is depending on the mass of the planet and the period also. But if you are interested in lower mass planet, you need to have more and more precise instrumentation. And here, this is a picture of an observatory north of Chile in the middle of Atacama Desert. And this, you have 4 8-meter telescopes. So the mirror, the main mirror, has a diameter of 8 meters. So we have developed an instrument with the capability to collect the light coming from all these instruments and to measure the smallest change of the velocity you can dream. And you see, this is just a cartoon to show, and the goal of this instrument is to achieve 10 centimeters per second. Why 10 centimeters? So small change of the velocity of star, because the Earth is able to change the velocity of the sun only at the level of 10 centimeters per second. So if you are interested in this category of rocky planet similar to the Earth, you need to have this extreme high precision. And the goal of this development is to maybe give an answer: do we have Earth twin, and do we have life on some of them? And this could be probably a very important revolution in science if we realize that life is only existing on this Earth planet, but also exists in other parts of the universe, maybe quite different from our one, we do not know. And maybe we are just at this moment that the technology gives the possibility to address this kind of questions. Okay, this is just to illustrate the forest of atomic transition we have. Okay, it looks easy to say, okay, we need to measure, but the amplitude of what we need to measure is 10,000 times smaller than the thinnest of these characteristics. So it's really, really difficult. It corresponds to a motion on the detector of about 1 atom. And what is worse, stars are not perfect. This is an image of the sun taken in a specific wavelength. And you can notice in the small rectangle to the upper right that you have a small dots. And in the middle, we have a blue one. And this is at the same scale as this image, the size of the Earth. So let's imagine we need to see the change of the sun due to this small blue dot, or to see the crossing, the transit of this small blue dot in front of the star. So this is a technical difficulty to search for rocky planet with maybe life. And at the present time, we have some technique that permit to allow the determination of the chemistry of the atmosphere of this planet. It's maybe a little bit technical to disturb. And the one part of the activity of my colleague presently, and this will be one of the highest topics of the next decade, will be to search for molecules related to the life, as we believe. So we start to analyze the chemical composition of the atmosphere of exoplanet with temperature compatible with the chemistry of the life. You have seen already that beautiful kind of instrument we have at Paranal with this 4 telescope of 8 meters. You see that, for example, also the Atacama interferometers. And this is just to see the progress of the instrumentation made during the last century. In the extreme right of this, you have a arrow, red one, pointing towards a telescope, is historical telescope, is the Hale telescope, is the Mont Paranal. When I started my studies, this was the largest one. The size of the mirror was 5.5 meters, and people believe this will be the largest we can build. And today, presently, in Atacama Desert, you see the ESO ELT. This is shown by the green arrow, and the mirror will be 39 meters of diameter. So let's imagine okay, it's not one single dish, it's a small cluster of smaller mirrors set together, but with extreme precision, because you need to have a perfect dish at the end. And this is not fiction, because here you have an image of the status of the development of this project made in about 1 year ago, a little bit less. And if you have good eyes, have a look just in the middle of this, the foundation. You can see two men, one in green, one in red and one in blue. Just to give you the size of this thing. It's absolutely incredible. And if things are going well, we expect that the first light, the first measurement to be possible with this instrument will be in 2028. So we are not so far. Evidently, you probably have heard about the James Webb Space Telescope measuring already from a few months. It's a smaller telescope, 6.5 meters, but in the sky, above the atmosphere. So, and measuring in infrared. So this is absolutely a fantastic instrument. And I will, it's not completely finished, but one of my last slides is this, evidently it's a super picture, because this is one satellite, a spacecraft, sent a few years ago, took a picture where a satellite of Saturn was just at the position to do a perfect eclipse of Saturn. So what you see here is basically the ring surrounding Saturn. So this ring are a huge number of pieces of rocks and ice, small pieces of ice. But this is not the most important. The most important is this very small blue dot on the lower part here. And this is the Earth. So if you are only at a very small distance, maybe half an hour of light here, the Earth is only something like this. So this is just to maybe consider, we have to be modest. See, the Earth is really a small rock at the size of the universe. And I will finish with a small calculation, estimation we can do together. As you know, that Apollo 11 moved to the moon. In the travel need 3 days, but the light need only 1 second to do it. So let's imagine with our current studies, we will discover a perfect planet with a good temperature, with a chemistry maybe convenient for life development, at, let's say, at 30 light years. 30 light years compared to 100,000 light years of the galaxy is really one of our neighbor. Let's imagine you can find such a potentially beautiful place to go. But 30 years is already 1 billion of seconds. So this is already 1 billion times more distant than the moon. So the dream mentioned sometimes that the humanity could move, emigrate to such a planet is completely crazy. It's not possible because the travel, okay, you can say, oh yes, but we can accelerate. But if you want to accelerate, you need energy. And the energy to increase the velocity to maybe 11 kilometers per second of the Apollo to maybe a fraction of the luminosity of light, it's completely crazy. So we don't have any real possibility to emigrate of the Earth. And maybe Mars is a different story, but at least for extrasolar planet, I don't see any possibility to do it. So it's not pessimist. Some people say, oh, you are pessimist. No, life is a beautiful planet. No, the Earth is a beautiful planet. So thank you.
Thank you very much, Michel. Thank Thank you very much. Stay with me. So we're going to have a few questions. So we're going to open the floor for questions. I've got a few for Michel. So I can start the series of questions. You talk a lot about Chile as a place where we can observe other planets. Is there a good reason why Chile has been chosen?
Yes, Chile is not the only place where we can do a high quality astrophysics, but Chile has a specific meteorologic condition. You have a current, the Humboldt current, going up along the coast of South America, and is a cold current of water. So all the year you have a strong stratification. You have clouds of fog on the top of the ocean, but behind you have it's a desert. All the attack 3,000 kilometers along from north of Chile, Peru is a desert. And this is a perfect place for astronomers because it's a huge number of clear nights, low content of water, and stratification. You don't have too much turbulence.
Okay. And then you talk about the Earth as a rocky planet, and then you explain a little bit the different compositions. So it could be a gas, it could be water. Is that correct?
Yes, yes. Yeah. You have different category of planet. You have rocky planet. So it's relatively small planet because you don't have so much matter to form bigger rocky planet. Maybe it seems that we have a rocky planet up to 5 times the mass of the Earth. So this is typical. Then after you have a gaseous planet, like Jupiter and Saturn, could be 100 times the mass of the Earth. And you have a different family also, it's ice planet. So Neptune and Uranus are made mostly of ice. And also, evidently after you have combination, because if your ice planet migrates towards the old star, in fact, after it starts to be melted, and it's transformed in an ocean planet. Not our own ocean, but ocean. Most of the planet is made from water. So you have a huge diversity.
Incredible. So I invite everybody. I can see that there's no question asked on the. So you've got a Q&A function on your Zoom. Do not hesitate to ask any question. Do you have a few, Emma? Okay. Okay, excellent. You send that to me by my phone, and I will.
J'apprécie le support.
Excellent. So yeah, I suspect. So tell us about astrophysics as a field of research, but as a field of investigation. If we read the news today about the fact that in many ways, as you discussed, this Earth has been quite damaged. And of course, a lot of people are dreaming of another world, and you explained that you're afraid that this world is not reachable nowadays, and it will take a lot of energy and a lot of time to reach it. But is there, in your field, is there a renaissance of interest on astrophysics, and can you see more and more young researchers being involved in astrophysics?
Oh yes, certainly. The 20th century and right now, it's a beautiful period for astrophysics, because we have to realize that in the beginning of the 20th century, you have the Einstein discovery of the general relativity. You have the discovery of the origin of the luminosity of the sun. Let's imagine until 1938, we do not understood the reason why the sun was shining, and so on and so on. The origin of elements, of chemical elements, and so on. So the discovery of planets. So this is a fascinating. This is a byproduct of the technology, evidently. And no, we have a huge number of new students coming and entering the domain of astrophysics. And the total number at the size of the Earth is several thousand.
Yeah, exactly. So tell me, Emma, where is it? Okay. Okay, when it's coming.
And also two who have raised their hands and would like to speak. So...
Okay, no problem. So we know that there is no plan B. So why are we looking for another life? Thank you, Bodo.
It's a very interesting question, because I believe it's part of the curiosity of man. When you are searching in East Africa, the origin of mankind, you are not looking for any industrial application of that. It's just to satisfy the curiosity of man. And the fact to discover maybe that life exists in other parts of the universe, it gives some answer to our own life here on the Earth. So I believe it's simply one of the most important aspects of the human mind is to satisfy the curiosity.
There is another, but I did not, Joanna, can you rephrase a little bit your question? So I did not really understand the question, unless Michel, you get it. How did are you talking about astronauts, astrophysics? Okay, so let's answer this question. How did astrophysics make it possible to explore planets in the universe?
So this is the first, as I try to explain, this start to discover planets, and then after to develop instrumentation to analyze the mass, the size, the shape of the orbit, the chemical composition of the atmosphere, and to simply understand really what are the chances that we could have a form of life, or simply already to simply understand the mechanism of formation, exactly like a geophysicist try to understand the history of the formation of mountain. It's part of the science.
And I suspect, I mean, you started, I don't know, maybe 30 years ago, 40 years ago, your career, and there was at that time maybe instrumentation or observation of the sky was not as developed as it is now. So I suspect your work has also changed a lot from calculation and estimations to direct observation.
Yeah, I will just correct you on one part.
Please.
I started 50 years ago. And at the time, it's completely incredible that the most important detector at the time was photographic plate. And today it's completely different. You have a huge quantity of electronic, you have computers, you have satellites, you have so this is the rich aspect of the astrophysics of today.
And I suspect with big computers as well, you can do a lot of modeling as we do as well in medicine, but highly developed.
Yes, it's one characteristic of astrophysics. You cannot play in the lab with a star. You can, in physics, you can do some experiment in the laboratory, not in astrophysics. So you have to have a deep understanding of the physics and to try to apply this rule to body we're measuring in the universe. But evidently, you need to have huge computer, a good knowledge of physics, in the computer to simulate all what is going on inside a planet or a star.
A question from Bashir from Kakuma. How was the galaxy formed?
Oh, okay. At the beginning of the life of the universe, you have a strong expansion, very high temperature. And this is measured, it's not a fiction. At this high temperature, high density, you have only independent electron and proton. Then after, you have the combination of these, and gradually you form things more and more complicated. But at the beginning, it was extremely smooth. This was measured by satellite, Planck, for example, or Kobe. So you start to have small fluctuation, and due to the gravity, you have the coagulation and formation of structure. This is a global picture. To see after the details of the formation of galaxies is a very active domain of astrophysics today. Because in many of the galaxies, we have discovered a big black holes, a huge point of the universe where the gravity is absolutely incredibly strong. So to understand who it was the first, do we have first the formation of the black hole, and then after you accrete matter to form a galaxy? Or, okay, this is very active domain of astrophysics.
Excellent. Thank you very much. Please do send your questions online. We try to answer them.
Hello, from Kakuma. We have some more questions, but we are typing them in using the chat box.
Okay.
Yes.
Okay, good. Oh, fine. We just saw them. So question from Bodur. Thank you very much. So Bodur is studying energy engineering, but astrophysics or astronomy has always been a passion. Some piece of advice on what we have to do to work in astronomy or to study astronomy. What would be the best way of doing it?
So astrophysics is physics. So almost 100% of present astronomers or astrophysicists are people having studied physics first. So all my colleagues, myself, we have studied physics. And then after, you have to do a PhD in one lab and to find a position for that. This is, I would say, the classical way to go to do astrophysics. But it's not the only way to do it. For example, just have a look on the construction of a satellite, of a telescope like the 39-meter in Chile. It's a huge construction. So you have plenty of engineers, mechanical engineers, optical engineers, and so on, studying and helping to construction. Without all these people, we will not have the development of instrumentation. So if you are studying engineering, in fact, maybe you can find and see if at some moment you will have an opportunity to collaborate to the construction of a structure of a new instrument in astrophysics.
Mm-hmm. Then we can come to the question of Baha. But before that, in astrophysics, I mean, it seems that there seems to be some epicenters, Northern America, Europe. Is that correct? But what about, are there astrophysicians in the Middle East, in Africa, for example?
Yes, you have from a long tradition of astrophysics in South Africa. Because the European could observe at the time the Northern Hemisphere, but to go to and observe the South, they move at the beginning in South Africa. Yes. And in other parts of the world, you have a huge activity presently in China, India, and so on. So the astrophysics, okay, it's maybe more recent, but it's they are in Africa presently, except South Africa. But you have other places. I've visited a few months ago in the Atlas chain in Morocco. So yeah, it's much smaller observatory, but they are doing quite a good job also measuring some specific points. Evidently, they don't have the money to develop a 30-nanometer telescope, but something is also happening in different parts. Maybe not in the tropical part, because this is not the most easiest way to, the sky is not the most appropriate for them.
And Baha, so if we could twin the Earth, and after years we could overcome the energy challenge, what kind of other difficulty are we going to face? And what about this discussion about colonizing Mars?
So Mars, do not have an atmosphere or extremely small atmosphere without oxygen. So it's something equivalent of the pressure we have at 80 kilometers in the Earth's atmosphere. So, okay. And you have no oxygen. The ground is toxic. So contrary to some film we have, it's fiction, you cannot plant salad on the ground. No, it's the worst desert on the Earth are completely paradise compared to Mars. So, and then after, what is the reason to go? And for example, Elon Musk mentioned the fact that maybe in 1 century, he dreams that 1 million people will emigrate to Mars. Let's imagine the energy and to be put by the whole humanity to send this 1 million people. And I believe it's completely stupid things. I don't believe at all. And who will be elected to go if it's to save because the Earth is no more habitable? No, I believe it's. I can bet that we certainly not have such a development. To go to Mars with maybe few person, like Apollo 11 for the moon, yes, certainly this will happen, but not the migration of the humanity. And the Earth is, okay, have some serious problem, exactly, but this problem is much easier to solve by the humanity than to emigrate to Mars.
Question from Nazreen about dark matter.
Dark matter. So this is not directly my field of competence. Okay, this was discovered by Dirac many decades ago, that you have, for example, you have some particle like the electron, and you have another particle with exactly the same characteristic, except the charge of the electron. And this is true for other particles. So this is still a very important question in astrophysics. So at the formation of the universe, why we have not formed a mix of two forms of particle in 50-50? Why we are living right now in one universe, mostly from this kind of matter? Up to now, I don't believe this was answer. And we observe sometimes some different kind of particle, but in negligible amount. So, okay, I don't know. This is part of the big question of science. It's good, in fact, to have big questions for the young people, for
the new generation.
Yeah, exactly.
To follow your feet. Thank you, Bodo, for the encouragement. Thank you very much. Okay, a question, Joanna, a question about Earth, but I think it's not about astrophysics. So we're trying to find the right expert for you about the formation of continents and so on. What is the main force that rules the universe? That's a big question.
Evidently, the most important is the gravity. The gravity, it's a force extremely small at the level of the small mass and small distance, but at the large distance and large quantity of mass, this is really the domain of the gravity. But evidently, the detail after the interaction are concerned electromagnetism. But for the universe, I believe this is gravity.
Thank you. A question from Rashid about what is the furthest exoplanet detected?
La plus
lointaine.
Ah, la plus lointaine, oui, oui. Okay. Already something like 15 or 20 years ago, some colleague mostly from Poland tried to observe a field in the center of the Milky Way, taking pictures and pictures and pages, and with the same ideas as the Kepler satellite to search for transiting planet. And in fact, they have discovered quite a few of planets at some kiloparsec, so some very big distance from us. But I can criticize a little bit because I'm part of the paper. So these objects are interesting, but what you can do after, they're so faint. You cannot analyze the mass, you cannot analyze the chemical composition. So on the aspect of the symbol, yes, we have discovered planets extremely far, but I'm convinced that the most interesting for further study are the closest one.
So what's the difference between a planet and an exoplanet?
Oh, easy. In the solar system, you know that we have 8 different planets. So they are relatively close of us. We know the name of this. And exoplanet is simply, if you have to keep in mind only one thing of this webinar, is an exoplanet is a planet hosted by a star different from the sun. So you look the sky, you see this huge number of stars, and you ask yourself, do we have planet hosted by this star? And an exoplanet is simply a planet hosted by a distant star.
So it's basically an exoplanet is a planet that is not from the solar system.
Exactly.
Okay, good. Thank you very much. Okay, that's it at the moment. So we can wait for a couple of minutes. If there's no further question, we can maybe we come to a natural end. There are a few more coming. Why we do not consider Pluto as a planet?
Very interesting. Because during several decades, Pluto was considered to be a planet. And maybe 20, 30 years ago, astronomers start to discover new objects with distance more distant than Pluto, and with mass not so different from that. So the question, where we have to put the limit? And people try to define some limit. Pluto is really a small one, and with a very strange orbit, cutting the orbit of Neptune. And so at the present time, this family of new objects, and Pluto itself also, are considered to be asteroids, what is called a new set of asteroids, Kuiper belt, so outside of the solar system. And as a result of that, Pluto was no more considered to a standard or normal planet. And so, okay, I believe it's only a semantic point. You have a lot of things orbiting around the sun. So some are big, some are small, and then after it's a detail, the classification.
Okay. There's a question about, is there a possibility, so we suspect that the sun, the mass of the sun is changing, and that, so a question about, is there a chance that at some point a planet is going to change the orbit and change its trajectory?
See, this is a classical problem of celestial mechanics. Are we sure that the solar system is stable? So you have, let's say, 8 planets, and they are orbiting around the sun, but they have small perturbation due to the neighbor. So, for example, Jupiter will slightly change the orbit of the Earth, or Venus will interact also with so on. So it's some kind of big game, and we do not know. It's not a very difficult question, because you have not to do the calculation for 10 years, 1 million years or so. It's billions of years. And we cannot solve it by calculation. You need to have a strong computer to do it. And at some moment, the precision of the computer will not give the answer. So if you change a small amount on one detail, this changes the solution. So at least on a scale of billion, the solar system is stable. But in different situations, yes, it's true that we perfectly understand that in some cases, this kind of BR or game and so on will kick one planet and take out, but not really with the star itself. We have the possibility to have the engulfment of a planet by the star, but this is mostly due to tidal effect.
Right.
It's a different problem.
Okay. And what about the trajectory of the solar system within the universe? Do we have a sense that distance between the sun and other stars, do we have a sense that this distance is not changing, that it's stable, as you said?
No. If you have the Milky Way, it's a huge disk of 2 billion of stars all around, orbiting around the gravity center of the galaxy, the Milky Way. But it's not easy to fill the point. It's mostly empty. So if you imagine that, because they don't have exactly the same orbit, so they are crossing each other and so on, but 200 billion of stars moving during 10 billion of years, no collision. It's mostly void. Yeah, the distance between stars are so huge that the probability of collision is nothing.
Excellent. There's a question about the universe expanding. What is the evidence about that, and what does that really mean?
Yes. This the universe is expanding. Is one of the most important discoveries of the 20th century. At the beginning of the 20th century, astronomers start to measure the Doppler velocity, measuring the velocity of galaxies. And at some moment, they discover something strange. The velocity is increasing. If the distance increased by a factor 2, the mean velocity increased by a factor 2. So this was typically what we have when we are in the medium where an expansion. And at the same moment, rather, people starting with the equation produced by Albert Einstein, that they found a solution that if you try to apply the theory of the general relativity to the whole universe, you discover that you have two possibilities. One, it's an expansion or a contraction. And this, suddenly you discover the same phenomena from the theory or from the observation. And today is more and more confirmed by a huge quantity of observation, and we can analyze the expansion, and worse, that maybe 15 years ago, you see that the most distant galaxies start to still more increase their velocity. So it's a huge domain. This is called cosmology. So the study of the evolution of the whole universe.
Excellent. So quite a few questions that are a repetition of the above. So I suspect we could make an end to this conversation. Dear Michel, thank you very much for taking the time to talk to us and share your knowledge. I also would like to thank Christelle and Shafia for the interpretation. Thank you very much for offering your time as well to make that possible. I just wanted to keep you informed that a recording of this session will be available on the InZone website. We also have your email addresses, so we will inform you when the recording will be available. And we hope you like this session. Please give us some feedback. And in September, we'll come back with a new topic and with a new expert from University of Geneva. And in the meantime, I wish you a very nice day and thank you for joining us today for this conversation. Thank you very much. Bye-bye.